So we don't need to remember to make that negative. If we had started down here at the 1, -1, going upward, that's a negative cosine result. So we'd be starting in the negative and have to make our coefficient negative. Okay, the first big one is going to be this period. The period, we could go from any point to the repeat of that point. So we could go from, we could go from anywhere. We could go from this point to where it happens again and count our period. But it's really tends to be easiest to go from either a max to a max or a min to a min to find your period. They're just usually easier to pick out. So that period looks like it's 6 units. So does that make our B 6?
No.
No. Our B has to cause the 6 to occur. We know that our period is
pi over 3.
Well, let's build that. Our period we know is supposed to be our natural period, which in this case is 2 pi, divided by that compression factor. And we need this to equal 6. And that's going to allow us to solve for that B. So 2 pi over 6 is equal to B. If we multiply by B and divide by 6. So, Corey, that's your pi over 3. So we got our A and our B. Now, because we're being asked to put it in this form where the phase shift is isolated from that compression factor, that B, we don't have to get too fancy. That H, I think yesterday when we talked about it, I said a lot of books use a lowercase c as opposed to a capital C for that. I always hated that. The H is better. It's a little more distinct. So that H is going to be our start location, our amount of phase shift. So that amount of phase shift is -2. We're back by 2. So that's going to make that H a -2. Do be careful. That X minus H is going to turn into an X minus -2. So it's going to turn into an X plus 2. Of course, it's going to do it over here in our cosine version. And how much is our lift? Well, that K, that lift, is where our center line is. So our center line is here at 0. So our K is just equal to 0. That all seem reasonable? I don't know why we lost a bunch of people. They seem to have trouble getting back.
There's a very big power outage. I currently am on my phone doing this, but there's a power outage like at my little sister's school. I'm out in the Applegate Valley. We don't have power. Out at New Hope Road, I know a family that doesn't have power. So I'm pretty sure that would be the reason.
That seems reasonable.
Yeah.
Well, as long as we don't lose power here, I can make sure this recording goes up. All the other recordings should be up. But yeah, that's unfortunate. Thank you for letting me know. So when we put this all together, we end up with y equals 1 times, we don't necessarily have to write the 1, but just for clarity, 1 times the cosine of the B we found was the pi over 3. And they want it in this X minus -2, so plus 2 plus 0. If you don't have to write the plus 0, you don't have to write the 1. That's all our pieces in there. Now, this is the form they asked for, so I wouldn't mess with it. Again, I wouldn't write the 0 and the 1. But if you were going to use this in applications, you would probably distribute that pi over 3. It just ends up being easier to work with for a lot of, when you're using a lot of tools. So, but do make sure if it asks you for this particular form, give it that particular form. So anything crazy in there? It's just, yeah, it's just being able to kind of work backwards from that. Now, the word problems can often seem like they're a little bit more difficult, but one of the things that I'm going to encourage you to do, you can probably guess based on some of the other things I tell you guys a lot, is if it's easier to go from a graph than from a word problem, if you're given a word problem, make a graph from it. So what are we told? Well, the outside temperature over a day can be modeled as a sinusoidal function. Say the high temperature for a day is 87 degrees. So that gives us a high of 87 and a low of 73. So we're going to have a low of 73. So my axis isn't going to be way down there. And the low temperature, well, let's see. Wait, suppose you know the high temperature of the day is that, and the low temperature is that, and the low temperature occurs at 5 a.m. Okay, so at 5 a.m. is where that low temperature is occurring. Okay. Assume T is a number of hours since midnight. So this T equals 0 is our midnight. Which makes 5 a.m. 5 units out. Okay. Find an equation for the temperature in terms of T. High temperature. Hours since midnight. Find an equation for the temperature. Okay. So, what do we know? Well, we know we should be able to figure out what our amplitude is because we know that low and high, right? So the low to high, the variance here, that 87 minus 73. What's 87 minus 73? Was that just a nice little, no, it's not. 714. Does that make our amplitude 14?
Nope, it's 7.
So our amplitude is the displacement from center. So our amplitude is going to be half of that. It's going to be 7. So looks like our A is going to be equal to 7, though we might have to make it positive or negative depending on what we do. Excuse me. So that also tells us then where our center line is, because our center line is 7 from each of those. So that means our center line is at 80. So our lift has to be 80. Well, that's 2 of our values. We're halfway there. Okay, that's the easier 2. So, but still, it's 2 of our values. We're halfway there. Now, what about period? It might feel like we're not told a lot about period, but we are told that this temperature varies over a day, right? So our period, this thing has to repeat every day. Fair? And we're doing time in hours. So if we're doing time in hours, what should our period be?
24.
Should be that 24. So our period is our nice 24 hours. But we know our period is supposed to be 2 pi divided by that compression factor. So if we want 24 to end up being our period, we got to find the b that's going to make that work. Again, multiply both sides by b, divide both sides by 24, and we get that nice pi over 12. So for a period of 24 hours, we will need a compression factor of pi over 12. Is that all fair so far? Now, one of the easy errors to make when doing a problem like this is this 5 a.m. can often throw people off, because what people often want to do is say, okay, then we start at midnight and reach that minimum at 5. And then we continue, through our oscillation. But do we know that we were 80 degrees at midnight?
No.
No. And we frankly have no reason to believe that. So we don't know if this thing came from before then, came from after then. So we don't know when we hit that equilibrium point there. So we can't really use that y-axis very effectively right now. We do know that we were at this minimum at 5 a.m. and we know what our period was. Our period is supposed to be 24 hours, right? So this is going to be, 29 hours later. That's going to be the next 5 a.m. Fair? So if we wanted to graph one period, that's where our one period is. This maximum would have to be halfway through. So that maximum would be 12 hours later. So that would be at 17 hours after midnight, or 5 o'clock in the afternoon. Well, if we know that this is 5 and that's 17, or that this distance is 12, then, hey, we can suddenly say we know where that middle point is. That middle point has to be at 11. It's got to be 6 hours later, right? A quarter of our period. So where did this actually hit? It hit up here at, -1 hours, or 11 p.m. So that combination of the knowing the period because of the 24 hours and that kind of phase shift of 5 can tell us where all of those other points are, but be careful about making assumptions about things hitting your axes. Questions about that? Fernando, Abigail, Declan, you guys all okay with that? Now, we didn't have to backtrack to figure out where it hit that center line. As soon as we know we're hitting this 5 and going 24 hours, we could write a model, but just to kind of clarify that. Now, we've got to make a decision. Do you want to use a sine function or do you want to use a cosine function?
Since we're starting at a low point, we should use sine and shift 5 to the right.
So if you wanted to use cosine, if you wanted to start at this low point, We could use cosine. But we did just go to the trouble to figure out where that midpoint is, right? So we could do that too and use sine. It might be nice here to use cosine because that was the given piece of information, was this low at 5 a.m. But we used cosine in the last one, so maybe we should use sine. I don't know. You guys got a preference other than Corey's cosine?
Well, the thing is, if you use cosine, then you have to use negatives. If you use sine, you have to use the negative.
That is sine starting downward, so they're both going to end up being negative in their lead coefficients. No strong feelings?
I mean, I'd rather just use cosine.
I don't argue with that. All right, so if we're going to use cosine, we're going to have that amplitude of 7, but as Corey pointed out, because we're starting at the low, that A is going to have to be that -7. Our B is that pi over 12 that forces our period to be 24 hours. That D, our lift, is the 80 degrees. And because we've shifted over 5 hours, and it is nice to use because they gave it to us, so it's nice. So we do have a shift, and that's that H that they like to use, of 5. And that's in our A cosine B x minus H plus, I think they use K, unlike the D, either one, form. And I guess it wants a T, so we should use a T. It told us to use T. So we should use a T. So -7 cosine pi over 12 times T minus 5 plus 80. And that would really be fine, I suppose. You have probably gotten used to the idea that I would tend to distribute that. That's probably more of a personal preference, and a personal preference born from when you start using these functions to do calculus or do other modeling or use other tools, it's easier to work with from this secondary form when it's all multiplied out. But boom, that's our model. If we want to find what the temperature is to the nearest 1/10 of a degree at 10 a.m., you're just going to take that and throw in a 10 and get some number. Remember when we used to use that for number and call it the pound sign? Had young students say, "Why'd you put a hashtag there?" Or old-fashioned symbol for number. And you'd have to tell me what that is. I'd have to put in a calculator. But it should be, what, less than 80, more than 73. So my guess would be 78, 76, something like that. And you could certainly use that equation to do it.
I got 78.2 degrees.
78.2. Okay. That seems reasonable. So if 11 hours was at 80, that 10 hours being at a nice 78, I totally believe that. Hey, questions about either of those things? I'll take it. That means you guys are happy. Do you guys want to try one like that on your own? Or let's do that just to be sure. Why is it not working? All right. Sorry, I can cut off the word graph down there. So here we're particularly told a couple of points just to help us interpret the graph a bit. But given that graph and those points, since we've done everything cosine so far, let's enforce that we do it with sine, just to make us practice. And sine can be a little bit more difficult because you need that center. So I don't think we'll be bad on this one. But take a minute and determine an equation for that function.
We lost Declan, but I think that's because he's on his phone, so he might have ran it. His phone might have been low power.
Ran out of juice. Well, I didn't lose power. Why didn't I get to lose power? No. No, it's just still symmetric. That's too bad. That's okay. No, those maxes are a little bit tough though. So sine's actually a really good choice for this one, because trying to figure out like exactly where that maximum is it 1.5 or 1.25? So that maximum's a little bit hard to read. But knowing that it does go through this point exactly, because we're told it does, and this point exactly, does give us a nice period of 14. Which implies we have a B value of, what does that make our B?
5/7.
Over 7. Now, what about our phase shift? How much is this thing shifted?
-2.
Good. -2 is a nice choice. It's not one of the points we're given, but we certainly know that that point, it has to go through that point because that is half of our period. So it does go directly through that point at -2. That gives us a small phase shift. It is generally nice to use the smallest phase shift we can, not always, but by default. And that keeps our sine function positively oriented, which is also nice. But could we do this with a phase shift of +5? Sure. Could we do it with a phase shift of -9? Sure. We could do it with a phase shift of -16 if we wanted to. They're different functions, but they will produce the same graph. Just like you get angles that are coterminal. They're different angles, but they have the same terminal point. It's same thing going on here. They're different kind of time stamps, but it's the same function or makes the same graph. But I totally think that that phase shift of -2 is totally reasonable. And we could use that with an H just of -2 if you want to use that form. Or our C would be the -2 pi over 7 if you wanted to do it distributed, but we can just build that by distributing it. So we'll just distribute it. Oh, and lastly, I suppose our lift or vertical shift is kind of the boring 0. You guys happy with all those? All right. Then our function turns into y equals, since you told us to start here, we are nice and positively oriented. So +3, and we're using sine pi over 7 times x minus the positive, or x minus the -2. That is something to always be careful of. Plus 0 to be complete. You don't have to write that. So y equals 3 sine pi over 7 x plus 2 pi over 7. And again, the computer often likes it in that top form, but I just apparently can't emotionally stand leaving that alone. Questions about that? So depending on what you end up doing with your waves, sometimes you'll more going from the function to wanting to know how the graph is behaving and how it's oriented. Sometimes you end up needing to go the other way more often. Just depends on what focus your particular discipline has. For those of you who are doing the medical imaging or kinesiology, more the medical imaging, especially this kind of wave dynamic and wavelength frequency stuff that we're kind of getting into here is a lot of what those programs want to make sure you see. So if you're in those programs, this is a good section, a good couple of sections to make sure you're really focused on, because that's one of the reasons you're here. Okay, so we should probably talk about tangent at least a little bit. I want to remind you about a couple of things about tangent that we've talked about. We think of tangent, and certainly should think of tangent, as the ratio between that y and x value there. So the tangent of some angle theta, we know by our circular definition, is the ratio between the y value there and the x value here. But if you remember back sometime last week, we talked about the reason it's called tangent, and one of the more important geometric meanings of tangent is that the tangent value is that physical length of a line tangent to the circle up to that ray of that angle. So this physical length is going to be the same as that ratio y over x. And we talked about why that has to be true based on similar triangles. And the reason I want to remind you of that is because when we're thinking about what the tangent graph looks like, it's often easier to think about it in terms of this height. Because if we start our angles at 0 radians, you could certainly see that this height, that physical height, would start off being very, very low, would start off being 0. And as that angle increases, that height is going to increase. So, okay, this function is going to get bigger and bigger. And it's going to get very big after a while. The larger this angle is, the longer that tangent length is going to be. And back to our ratio, if you prefer, if this is our y value and that's our x value, you can imagine the ratio between y and x, y is going to start becoming a lot bigger than x. Like even right here, it might be 4 times, y might be 4 times the value of x, meaning our tangent value would be 4. But as this gets steeper and steeper, that length and thus that ratio starts getting quite extreme, to the point that when we're considering an angle at pi over 2 radians, or at 90 degrees, well, how long does that line have to be? Let me redraw this. How long does that pink length have to be for it to hit an angle that is going at pi over 2 radians? Well, it doesn't matter how long it is. These are parallel now. They're never going to hit, right? And even on our unit circle there, our x value and our y value, their ratio would be 1 to 0. that ratio is undefined. Why is it undefined? Well, it's undefined because it's trying to model where something hits that doesn't hit. Does that seem reasonable? So this thing gets larger and larger and larger and larger, sure, but it does end up having that nice asymptote at pi over 2. Fair? Now, you could visualize this. We'd keep drawing it and visualizing it out. But I've got a nice little GIF for you here that kind of models that. So notice as it continues to go around, I'm going to leave that over here. As our angle continues to go around, oops, that went away, sorry. But let's do it anyway. As our angle continues to go around this direction, and we got our circle, and we want to know, okay, how high on this line tangent to the curve? Well, this ray never hits that blue line, but if we let that ray go in reverse, it certainly will intersect that tangent line down here somewhere at some distance. That distance is just negative because it's going downward now. And when we're near pi over 2, that distance is going to be quite large. As we get towards pi radians or 180 degrees, that negative distance is going to be really low. And again, that's modeled by a nice asymptote. Let me bring back that nice picture. There it is. I like that picture. And we know our tangent values in quadrant 1 should be positive. In quadrant 2, they should be negative. In quadrant 3, they're back to positive. And it's all in this diagram, all about kind of measuring that length. Now, when we talked about tangent before, I talked about, imagine, turning our heads to see a train as it goes by, or things like a spinning light shining on a wall. Like when the cops are arresting you down an alley, happens to everybody, right? And you're sitting there with the handcuffs on you, and all you can do is watch the light spin around on the alley walls and think about math. I don't know how things work. That's kind of what some nice physical representation of what that tangent graph is doing. So that ends up giving the tangent graph this fairly recognizable shape of having these big repeated sweeps. And they're asymptotes. Oops. And again, if that's at half a pi, that's at pi, that's going to the next asymptote at 3 pi over 2, then that center at 2 pi, and so on and so on and so on. Now, some interesting things that happen as a consequence of that, let me pull that up here, is that when we graph tangent, we often like to graph it instead of like this, kind of thinking about all these kind of broken up pieces. We tend to like to graph tangent on both sides of the y-axis, because that one sweep of tangent gives us all of those values. That's kind of one period of tangent is one of these sweeps. Sweeps isn't a technical term, by the way, but one of those curves between two asymptotes is the repeated period of tangent. So instead of drawing it broken up, it's often handy to draw it mirrored, or not quite mirrored, but centered across that y-axis with an asymptote at pi over 2 and the other asymptote, instead of being over here at 3 pi over 2, have it be over here at negative pi over 2. That seem reasonable so far? One of the big consequences of that is our period for tangent isn't 2 pi. Sine and cosine repeat themselves every 2 pi, but the one repeated piece for tangent is actually only 1 pi. It's got a smaller period to it. So that's actually kind of handy later, but it is something we've got to be at least a little bit careful of now, because we're so used to thinking of our periods as 2 pi. As soon as you're talking about tangent, it repeats every pi. Also, the idea of amplitude, that amplitude being how high and low does this function go, we kind of lose the idea of amplitude. There is still sort of an idea of amplitude if you want to put it in there. We don't tend to, but if you look at, if you imagine our defaults for an amplitude of 1, this function will pass through that 1 at its quarter. So at a quarter of the way through, it'll pass through that -1 exactly. Well, didn't draw it real well, but that's okay. Exactly a quarter of the way through. So if we have a tangent graph and we say put a 4 tangent of x, well, that means what's going to happen is it's going to take this normal curve and stretch it up so that that quarter point happens at 4 instead. It's nowhere near as significant as the max and min amplitude for sine and cosine. It's just, okay, it's stretched out a bit more. Here's where that stretch is. We really don't ever ask you to find that. So amplitude, we almost can just ignore the idea of amplitude when we're talking about tangent. It is in there, and if you're interested, finding it isn't hard. It's just we don't tend to focus on it because it doesn't mean very much. But really, other than that, the nice thing is if somebody comes along and says, hey, graph y equals, I'm going to say 3 tangent of pi over 2 x minus, let's have some fun with it, 3 pi over 5. I don't know if that's fun with it, but I'm going to go there anyway. Plus 1. And you think, hey, we haven't talked about tangent long enough to do this. Well, actually, as long as we keep in mind the modifications that tangent has, all the stuff that we've learned from sine and cosine kind of apply to it. For example, we can say we have an amplitude of 3, though, as I said, we're not going to care so much about that amplitude of 3. It's going to make it a little more stretchy, but it's not actually going to affect our work. We can still figure out period the same way we did before, if we're careful. How did we figure out period before?
Pi divided by the k value.
Now that's what we did, but if you look back, that's not what I said when we did it. Remember, I always said take the natural period and divide by the compression factor. Our natural period was just 2 pi at the time. The only difference here is our natural period is now pi. So instead of doing 2 pi divided by b, we're going to be doing pi divided by b. But if you thought of it or tried to think of it as our natural period divided by the compression factor, we're still doing the same thing, just with a different natural period. That seem reasonable? And it certainly is something to be careful of. But that's going to make our period 2. Excuse me. For our phase shift, we could factor the pi over 2 out up here to isolate it, or we could just take that C value and compress it externally. Either way, we're going to end up with what, 6/5? Or again, you could factor it out up here, factor out the pi over 2 up here. And well, how do you factor pi over 2 out of that? You divide it and you'll get 6/5. So it's whether or not you're trying to divide it up in the equation or trying to divide it separately. You're still having to divide out the compression factor to isolate the phase shift. And we still have a nice lift or vertical shift of 1. So really in that list, the only thing that changed was the natural period for tangent is different than the natural period for sine and cosine. Graphing it is going to feel a little bit different.
So is this a longer session than usual?
Oh, no, I'm just being talky. Thank you for pointing that out. I just start talking and have fun. But let me, thank you for pointing that out. Let me finish this up super quick. So the big thing about tangent is that its period is centered about the middle. So that phase shift of 6/5 means we're going to be going out to 6/5. And then that period of 2 is centered around that phase shift. So 1 in this direction to 11/5 and 1 in that direction to 1/5 gives us our period of 2 and tells us where our asymptotes are. So making sure you split that period on either side of your center to find your asymptotes is important. We got a lift of 1. So that means our center is going to be there. Our amplitude of 3 means we're going to stretch it out a bit, but it's a positive 3, so it's going to go upward like it's supposed to. If it was -3, we would have to go downward, so that would matter. But it's just going to fit in there nicely. And we could go from this 11/5 out 2 more to what, 21/5. Put another asymptote there. Go out from the 12/5 to 16/5. That's going to be our next center. And so on and so on. So it's a very similar process, just got taken into account the differences for sine, or differences for tangent, sorry. Okay, sorry about going over today. Thank you, Corey, for pointing that out. I would have just kept blabbing until I figured it out. But hopefully that'll give you some tools to start playing with tangent. Tomorrow and Monday, we're going to talk about the inverse functions and any review stuff you guys want to talk about. If something comes up between now and then, let me know.
Did you say Monday was the test?
Yes.
So does that mean all the 6.6 homework, is that still due tonight, or is it going to be due Monday or Sunday?
I suppose I could move it. Yeah, I'll move that.
I mean, it's just not a huge deal. Just
Yeah, no, it'd be good for us to actually talk about it some before you have to do it.
Yeah, I need to know how to manage what assignments I need to do.
Yeah. So yeah, I'll move 6/6 out to Sunday or even Monday. Just
So
say do
the
it for the test.
the test isn't tomorrow?
Nope. Yesterday we moved it onto Monday.
Okay, that's good to know because yesterday my internet was going out, so I couldn't make it to the class.
I did post the video from that class online, so you should be able to go check that out if you want to.
Okay, cool. Thanks.
I'm just checking here, make sure it's there. Yeah, for 126. Yep, it's there. Okay.
How did you get there again?
Oh, it's just under our calendar
Okay.
on Math and Math. And they're usually closed up like that. So little block for videos.
Okay, I'll definitely go find that.
Cool. Okay. Well, you guys have fun. Something comes up, let me know. And I'll talk to you tomorrow.
Okay, thank you. Bye.
Bye-bye.